Okay, everyone, this is section 8.7, and we're going to use systems of equations to analyze romantic relationships. And give full credit for this idea to Stephen Strogates, whose book Nonlinear Dynamics and Chaos is just a wonderful textbook on all sorts of interesting natural phenomena. This is one that's more fanciful maybe, although it has some validity to it, but all sorts of natural phenomena, insects, movement of mechanical systems, and all sorts of things. Anyway, a great book. But this is his idea, and I'm taking it and kind of running with it in my own direction a little bit, but it's basically his idea. So, suppose you have two people, Xyon and Yara. I used them for X and Y. And we'll assume that Xyon identifies as a he and Yara identifies as a she, just so that I can use he and she as pronouns. And X of t is going to be Xyon's feelings for Yara, and Y of t is going to be Yara's feelings for Xyon. Okay? So the question is, how do they change? Of course, that's what the derivative tells us. How do they change depending on what the feelings presently are, okay? So A, B, C, and D are all going to be non-negative numbers, positive or zero. And so if I want to have a negative number, then I'll put a negative in front. So these could either be positive or negative out in front, depending on what kind of a situation I want, what kind of a relationship. So I'll go through various things in the textbook, and instead of trying to just repeat all of that, I'm going to go through two things. One is the last example in the textbook, and we'll analyze that carefully, and then we'll also do the first exercise, which you are responsible for if you're taking this course. And I want to show you how I want you to just exhaustively really dig into this stuff, not just answer my questions, but to really dig in and explore. That's my hope. Is that there are fewer problems to do, and I want you by this time in the course to kind of take responsibility for playing with it and exploring rather than just rotely answering questions. So the first problem then in the book, I should say it's towards the end of the section, is what happens when we have a situation where this is a 3 and this is a -1, and then C is 2, and this is 0. Okay, so you got positive, negative numbers, and 0. So that's kind of a nice thing that captures lots of ideas. Okay, so the first thing we should do is to try to explain what this means about the personalities. Okay, so what does this mean about the personality? I'll use the phrase going north to mean that the feeling, the sentiment is becoming more and more positive. That is, if it's love, it's going to become greater love. If it's a hatred, then it's going to become a lesser hatred and maybe eventually become love. So it's going north means that you're heading towards a more positive feeling, and going south is the opposite. Then it means you're going your love is either decreasing or your hate is increasing, is what going south means. Okay, so what's happening here? First of all, what about Xyon's feelings? Well, Xyon, basically, how do they change? They change somewhat relative to what the present situation is. If Xyon's present feelings are positive, then the change is going to be going north. Depending on that. If Xyon's present feelings are negative, that is tending to hate Xyon, or Yara rather, Yara. If Xyon's feelings towards Yara are negative, so this is a negative number, negative times a positive is negative. If the derivative is negative, that means they are decreasing, they're going south. So Xyon's present feelings affect how they're going to change. Yara's present feelings also affect how Xyon is going to change. Let's look at here. If Yara's present feelings are positive, if she loves Xyon, then what's going to happen? Positive times negative is negative, so that's going to be a negative contribution. That's going to tend to make Xyon go south. Okay? And conversely, if her feelings are negative, negative times negative is positive. So he's kind of interesting. If she kind of stands off and says, I don't want you, well, he wants to chase her. And so if hers are negative, then he goes into chase mode and he starts becoming more attractive. So they go north. See? So you can kind of imagine how these different personalities actually happen. And there are some, right? There are people who are attracted by someone who mutually likes them back, and there are also people who are attracted more to someone who either plays hard to get or actually is hard to get, right? And kind of standoffish, and that's the turn on. So you can see how these different numbers will play out. What about Yara? Well, Yara is not influenced by her own feelings at all, but she is influenced by Xyon's feelings. If Xyon's feelings are positive, then hers increase. If his are negative, then hers decrease. See that? So that's how you should understand that. You should be able to look at a system like this and explain the personalities, or conversely, if you are given the personalities, you should be able to come up with a system that describes it. Okay, so that's who they are. Now let's see what happens with their relationship. So first of all, we'll use 8.6, and we know from 8.6 that, let's see, what do we have to check? We have to check tau first of all. So if I want to, by the way, I can write this as x is equal to, just to get it all here, 3, -1, 2, 0. So there's my matrix right there. So, so what do we have? We have that the trace is equal to 3, and we have that the determinant is equal to 0 minus a -2 is +2. Okay, so if you check section 8.6, you will see that when the determinant is positive and tau is also positive, then you're going to get yourself a repelling node. Okay, it's repelling and it's going to be a node, and that depends as well on the fact that tau squared minus 4 delta is equal to 9 plus 8, which is 17, which is greater than 0. So these are the three things that among the three of them determine what kind of a situation you have. So this is going to be check it out, by 8.6, it's going to be a repelling node, okay? So we know what a repelling node looks like, but let's go ahead and do the rest of the analysis here. That's what I say. It's more than just doing the minimal work. Let's go ahead and play with it and see what we get. So let's first of all find the eigenvalues. So the eigenvalues, and the key here is going to be to try to do it in the minimum amount of space here. So it's going to be 3 minus lambda, -1, 2 minus lambda. And I'm going to skip some of the steps here just for sake of space, but you can check me out. I'm going to get lambda squared minus 3 lambda plus 2, which factors into lambda minus 1 times lambda minus 2. Okay, so you set that equal to 0, and obviously we have our lambdas of 1 and 2. So once we have our lambdas of 1 and 2, this is all old stuff now. We want to find the eigen vectors. And so if you stick in 1 here for lambda, you're going to get 2, -1, 2, -1 times xy is equal to 0, 0. And notice one of these is just like the other one, so you're going to get 2x minus y is equal to 0. And that gives us an eigenvector of 1, 2. You can let x be equal to t, and y is going to be 2t. And so I like to write it like this. I just like to put the two together so I can easily find them. There's the eigenvalue, and then the eigenvector is as I say, 1, 2. Okay, there it is. And let's do the same thing for lambda equals 2. Lambda equals 2. Subtract 2 down the diagonals and you get 1, -1, 2, -2. xy is equal to 0, 0. And again, you get two equations that are the same thing, so you can get rid of one of them and you're going to get x minus y is equal to 0. And so that's easy enough. Your eigenvalue is 2, and the eigenvector is going to be t times 1, 1. Whatever x is, y is going to be the same thing. So there you have it. Okay, so there we have everything now. So now we can, first of all, write our general solution if we want to. Our general solution is going to be alpha times the eigenvector 1, 2 times e to the t plus beta times 1, 1 times e to the 2t. And again, this confirms that it's a repelling node. And if you remember a repelling node, let's go ahead and graph it here. Okay, so the first thing I like to do is to graph the eigenspaces. So here's the eigenspace 1, 1 right there. And I like to just identify it here. This is when lambda is equal to 2. And then here's the eigenspace 1, 2. 1, 2 means you go 1 over and 2 up. So it's going to look kind of like this. Okay, and so this is with the eigenvalue of 1. Okay, so what's going to happen to the trajectories? Remember what happens from an earlier section. Wherever we start, let's just say we start right there. As t gets to be a large number, this thing is going to dominate because they're both going to get large, but this one is going to get large faster. So you're going to tend to become parallel to this eigenvector. So it's going to tend to become parallel here. So it's going to kind of head off in that direction. On the other hand, as t goes to minus infinity, if we want to go into the past, as t goes into minus infinity, then this one goes to 0 first, and this is going to be the one that remains. And so as you're going to minus infinity, this is the one that remains, and so it's going to look something like this. It's going to come in along there, and then it's going to end up going off like that. Okay, that's going to be the general idea. Okay. And here it would do something similar. It would come in. If you started here, it would go off along here, but it would come in along there. Okay, so it looks something like that. What about something that started up there? Okay, well now, what happens? If you let, first of all, if you let t go to minus infinity, then you're going to come in along this one again, like that. Whereas if you let t go to infinity, it's going to head off along one of these, and so it's going to end up going, I've made that a little sharper of a turn than it normally would be, but it would be head off in this direction. And notice, by the way, that I'm never letting this thing cross one of these eigenspaces, because if it ever crossed an eigenspace, if we're ever there, then you play with it and see that anything that starts here is going to, or that it is right here, is going to continue right on that line. If you're right there, now you're going to continue right there. If you're right here, you're going to continue in this direction. So you won't be able to, you don't cross any of these eigenspaces en route, okay? So let's see, I guess there's maybe one more to do. What if I start, I think I've got them here. If I start here, let's see, which is the one? This is the one I want to go to. If I'm coming like this, something like that. Okay, so there you have it. Okay, so there's the different situations. So notice that one of two things is going to happen to the relationship. Depending on their initial conditions, they're going to end up in this quadrant, which means that this is X and this is Y. That both of their loves are increasing, right? They're both positive. They're both in the love quadrant. Each one of them is positive, and they're increasing. So they're increasing more and more as time goes on. Or the other possibility is that they're going to both end up in this quadrant, the third quadrant, which means that they're both going to be negative, and they're becoming more and more larger and larger negative numbers. See that? So they're gonna head down there. So it all depends on where they start. See that? If they happen to start right here, they're going to go in this direction. If they start right there, they're going to go in this direction. Now notice that this is effectively the line y equals 2x here, because the y value was twice as high as the x value, okay? So let's find a couple starting positions which should get us to go either this way or go this way. So here's what I did, and this is the kind of thinking I want you to do as well. I chose 3, 2 to be something in here. Notice 3, 2. 3, 2 is, let's see, 3, 2. 3, 2 is going to be 3 over, is that, let me make sure I did what I wanted here. 3, 2, yeah, I actually written down 2, 3, but I want 3, 2. So if I go 3, 2, it's going to be something like this. It's going to be 3 over and 2 up. Okay, so it's going to be right there. On the other hand, if I take 3, 7, 3, 7 is going to be 3 and 7 up. And notice, I'm with apologies here, I'm going to have to get rid of this now, just because I'm out of space, unfortunately, okay? So 3, 7, let me write it down here. X of t is equal to alpha 1, 2 times e to the t plus beta 1, 1 e to the 2t. There we go. Now I can get rid of it here. Okay, and I have a little more room for my picture. Okay, so I chose 3, 3, 7. So 3, 7 is going to be up here. See this point right there is the point 3, 6, because this line has slope 2, and that was this eigenspace right there. So by choosing 3, 7, I realized that I was over in this area here, which is going to end up going down that way. Okay, so let's check it out to make sure that this in fact works the way I expected. Okay, so if you started at the point, if the initial condition is at the point 3, 2, then you're going to get, look at here, then you're going to get alpha at time equal to 0. You're going to get alpha plus beta is equal to 3, and you're going to get 2 alpha. If this is 0 here, you're going to get 2 alpha plus beta is equal to 2, and then you can subtract one equation from the other, and you're going to get this minus this is going to be alpha. These go away, is equal to -1. As soon as you get alpha is equal to -1, then you can get beta is equal to 4. And so you're starting at this point right here, which is the point 3, 2. And so you ended up with this thing right here is a -1, and beta is 4, which is a positive number. Okay, so what's going to happen as time goes on? This is you're basically you're going off to infinity. So as time goes on, you're going to become kind of parallel to this thing right here. And notice that that's a positive number, so you're going to be going off in the direction of this eigenspace. There's the eigenspace 1 with the eigenvector 1, 1, and so you're going to be going parallel to that. And this is positive, which means you're going to be going off in the positive direction as these values get larger and larger and larger. Okay, so this is positive there, so you're going to be going off in this direction. Okay. On the other hand, what happens if we start at the point, what did I say, 3, 7? Then you're going to get, then this is alpha again, and this is beta. And so you're going to get alpha plus beta is equal to 3. 2 alpha plus beta is equal to 7. And so you subtract one equation from the other. And you're going to get, subtract here, you're going to get alpha is equal to 4. And you're going to get beta is equal to, then, if alpha is equal to 4, beta would have to be negative 1. So now alpha is equal to 4. And the key is that now beta is negative. See this? It's now negative. So what happens? You're starting right there. As time goes on, this is the one that's going to dominate again. Let me make sure that you're still with me. Yep, very good. This one's going to dominate. As time goes on, you're going to become parallel to this eigenspace here, and it's negative, which means that you are heading in the they're heading in the negative direction. So you're heading down this way. See that? So you take 1, 1, and you multiply it by a negative number, and you got a vector that's heading in this direction. So sure enough, that's just what we have. So so what does that tell us about the relationship? It means that given these personalities here, their whole long-term relationship is going to depend on what their initial conditions are. Okay, and that's true for a lot of these differential equations. That the initial conditions really determine what's going to happen. And so either you're going to be heading up this way, or you're going to be heading that way. So this is the kind of analysis I want you to do. I just want you to have fun with it, play with it, see how much you can do. Ask questions and answer your own questions. Okay, become inquisitive, and really play with it. Okay, really take it and run with it. Okay, so there it is. Anything more I want to say about this? Okay. To be honest, I realized I was wrong here. What I really wanted was I wanted something up here. I wanted 3, 5. So let's just do that one. Let's just do that one and see once what happens. You're on this side of this eigenspace, so it should end up going in this direction rather than in this direction. So let's just check it out. If we had 3, 5 here, so let's go back to alpha and beta here. If you had 3, 5, then what are your values? The key is what's going to be the value of beta. So you're going to get, if you subtract this one from this one, you're going to get alpha is equal to 2. And once you have alpha is equal to 2, notice, aha, sure enough, beta is going to be also equal to 1. So this becomes a 2 right here, and a 1 right there. And so sure enough, it's a positive there, and so you're heading off in this direction. Okay, so I'm going to make that correction on here. 3, 5 is the one I really want. 3, 5. Okay, very good. Okay, so anything else? Anything else there? So you can play with these things, and you can ask, what would they have to be so that they attracted rather than repelled. Oh, I know what I was going to say. So as I say, this depends totally on what your initial conditions are. On the other hand, there are other fixed points where it doesn't really matter. If you end up having a relationship that gives you this as your trajectory, then notice it doesn't matter at all whether it means basically you're going to get different trajectories depending on what the initial conditions are, but it's all going to have the same I can't remember which direction it goes, but it's all going to basically have the same direction, and you're just going to, or the same general pattern. You're just going to keep alternating from, in this case it would be what? This would be love, love. This would be love, hate. This would be hate, hate. And this would be hate, love, right? So, and you're just going to cycle between them. And if you started here instead, you'd get similar, except that all of them are more intense, okay? Here it's intense love, love. Here's it's intense hate, hate. And it all depends on where you are. But your starting point, I mean, whether you start here or here, tells you what the intensity is going to be. But it doesn't really matter whether you start there or there, because either way, the relationship is going to be doing the same thing. It's just going to be a couple days off, something like that. Same thing for like a spiral, right? If you have a spiral that, say, comes in like this, well, then it really even matters less, because no matter where you start out here, you're just going to finally come to the point where neither of them have any interest or passion towards the other one at all, neither love nor hate. See that? So there the initial condition really wouldn't matter much. So sometimes they do, sometimes they don't. Okay, now as I say, the next one I want to do is exercise 871. Okay, and again, this is just, I want to show you kind of what I expect you to do on these problems. I want you to have fun with them. So the problem I basically said is I want you to have a situation where, depending on the initial conditions, either they both go off love, love, or they both go off hate, hate. And what I decided was I wanted to come up with a situation where you have basically eigenvectors that look like this. Here's the eigenvector 1, 1, and here's the eigenvector 1, negative 1. And so I wanted a saddle point. I wanted a saddle point that looked like this. Okay? And so depending on where you start, you're going to do something like that. It's going to be a saddle point. Okay? So, given that this is 1, 1, here's what I decided to do. So it took some thinking. Okay? But I'm going to show you what I did. Okay, I said, okay, I want these to be my eigen vectors, and so I basically want my A, B, C, D to be such that when I take the eigenvector 1, 1, I want the eigenvalue to be 1 as well. And so this is better just give me 1, 1. If the eigenvalue is 1, that means that when I stick that into this matrix, I just get 1 times that thing. On the other hand, I want this to be an eigenvector with an eigenvalue of negative 1. So when you stick this thing into the matrix, I want you to get the opposite of that. See that? So I'm figuring out what do A, B, C, and D need to be in order to give me this situation. So I'm thinking backwards. Okay, this was a lot of fun as I kind of did this. Okay, so what do we get here? Let's multiply it out. A plus B has got to be equal to 1. Okay, if I look at this one, it's going to be A minus B. A minus B is going to be equal to negative 1. Okay, so that's got to be true for A and B. What about C and D? C plus D has got to be equal to 1. And C minus D. And by the way, I made a mistake here, right? Here's my eigenvector right there. This is a negative 1 right there. So I'm sticking this thing into the matrix, and I want to get the opposite of this thing. Okay, very easy to make mistakes here. C minus D is equal to negative of a negative is positive 1 again. Okay? So, what do A, B, C, and D have to be? Well, if you add these two together, you're going to get 2A. Did I do this right? Let's see. Oh, A minus B. Oh, I made the same mistake here. A minus B. A minus B. I have a negative there. Sorry. As I say, it's easy to make mistakes. A minus B is equal to a negative 1. Okay? So A plus B is 1. A minus B is equal to a negative 1. C plus D is 1. C minus D is also a 1. Okay, I think I've got them right now. Okay, let's check it out. So this is a negative 1 right here. So I get 2A is equal to 0, which of course means A is equal to 0. If A is equal to 0, B's got to be 1. What's got to be true over here? Add these two together, I get 2C is equal to 2. C is equal to 1. And so if C is equal to 1, then that means that D's got to be 0. So that means that my matrix is the matrix, easy enough, 0, 1, 1, 0. There's my matrix. There's the matrix that's better have these two things as eigenvectors and these as eigenvalues. Okay, I forced it to be that way. So you check it out on your own. You go through the process if you want, and just take this thing and find the eigenvalues. And once you find the eigenvalues, go ahead and find the eigenvectors, and you will find exactly what I have here. You'll find this is a pair, and you'll find this is a pair. Okay? There's a pair, and there's a pair. Okay? So, there it is right there. And so, what else did I do on this? I'm not going to go through all the work for you. But first of all, if you use section 8.6, you first of all notice that that tau is equal to 0, and delta is equal to negative 1. And if delta is equal to negative 1, we know it's a saddle point. So sure enough, that's again what I was hoping for, but that's verified by what we did in section 8.6. And we also can get the solution if we want. As I say, the solution is just going to be alpha times 1, 1 times e to the t plus beta times 1, negative 1 times e to the negative t. There's your general solution. And so I'll let you go through and kind of do the same thing I did with the previous problem, but you can see what's going to happen here. If you just want to start with any number, anything in the upper, the upper right-hand plane here, anything here, then if this was your initial condition, what's going to happen? If you're here or over here, well, I shouldn't say, it's over here. Everything over here, what's going to happen? You're going to end up having mutual love, right? So you go ahead and choose some if you want. Let your initial value be 1, 5, or let it be what? 4, negative 2, or 4, negative 3. 4, negative 5 would be down here, so that's going to do there. So just play with it and see what you get. Okay, so depending on your initial values, you're going to go here. On the other hand, if your initial value was say here, say it was 4, negative 5. 4, negative 5 puts you there. You go ahead and find out what alpha and beta are going to be. If you start off at 4, negative 5, you're going to end up going down there. Okay, by the way, let's be clear here. As time goes off to infinity, this one basically becomes meaningless. This is the one that's all-knowing and all powerful, right? This is the one that as time goes to infinity, this thing's going to go to 0. You're going to head off in the direction of this eigenspace. If alpha is a positive number, you're going to be going in this direction. If alpha is a negative number, you're going to be going in that direction. So depending on your initial conditions, it all depends on whether alpha is going to be positive or negative. And so you'll go off in one of those two directions there. Okay, one other thing to ask is what happens if one of these things is 0? What happens if beta is equal to 0? That means you start off right here or right there. Well, if you start off right here, you're going to be, your alpha is a positive number, which means you're just going to go straight off in that direction. If you start off right here, that means this is 0, but alpha is going to be negative. You're just going to be heading straight off in that direction. On the other hand, if alpha is 0 and beta is non-zero, if alpha is 0, then this thing doesn't apply at all, and you're going to be along this line right here someplace. Okay, then what happens? Well, no matter what beta is, if beta is positive, you're going to be over here, positive, negative, so you're going to be over here. If beta is negative, then these would flip, you'd be over here. But either way, what happens? As time goes on to infinity, this thing goes to 0, so you're just going to get sucked right into 0. So if you happen in this situation to have exactly the same values there, here and here, so that you happen to be right along this line right here, then what happens to your relationship? It just dies out. It just dies out to 0. So really interesting. It's not very likely. More than likely, you're going to have something that goes to one of the two extremes. But if you happen to be in a situation where you start off at 4, 4, let's say, or 4, -4, 4, -4. So one person's love is exactly equal to the other person's hate. Okay, Xyon's love is exactly equal in value to Yara's hate. Then, as long as they started off exactly the same, then they counter each other and it just dies to 0. So isn't that interesting? It's just really kind of cool to see how this stuff all plays out. So this is 871. I asked you to do something similar in 872, but I forgot what it is. But basically, try to do the same thing. Play with it. See if you can kind of determine what the eigenspaces are that you want, and then basically I think you can kind of do the same thing. But I know what I do in 872. I want it so that one of them hates and one of them loves. So what I'm after is I want it to look like this instead. Okay, yeah, that's it. So this is 872, where this is what happens. Okay, so go ahead. You can do what you want, but my suggestion would be do something like this, where find out what A, B, C, and D are, so that now this thing has the positive eigenvalue, and this one has the negative eigenvalue, like that, so that you head off. As time goes to infinity, you head off either in this direction or this direction. Okay? So do the same thing, play with it, determine what A, B, C, and D are, and go from there. So anyway, that's the way to have fun with these things, and I'll give you directions from Blackboard as to what else I want you to do for your homework. But a lot of neat stuff there. Okay? So there you go.